An enterprise deploys an artificial intelligence customer support agent. It is connected to the customer relationship management system, billing application programming interfaces, refund workflows, and internal documentation. It can look up customer accounts, issue refunds, escalate cases, and send automated responses. On paper, it looks efficient. It reduces handling time. It improves responsiveness. It appears to be exactly the kind of system organizations want when they talk about automation. Then one day, a customer discovers something interesting. By carefully phrasing a request, they persuade the agent that a refund is justified. The agent processes it automatically. Then they do it again and again. Within minutes, hundreds of dollars are refunded. No exploit was used. No credentials were compromised. No infrastructure was breached. The artificial intelligence simply used the tools it was given. This was not primarily a network failure, neither a firewall problem. It was not even a model hosting problem. It was a failure in the action control domain. My name is Giulio, and I work at the intersection of artificial intelligence security and enterprise architecture. On this channel, I am building a series around the artificial intelligence blast radius model. In the first foundation episode, I introduced the model itself and the 5 control domains that determine how far artificial intelligence impact can propagate. I also have published the episode, The Cognitive Control Domain, and examined how reasoning boundaries fail. In the last episode, the 1-4 knowledge domain, we looked at how retrieval and synthesis can expose information that should not have been surfaced. This episode moves outward again. Knowledge exposure is serious. Once an artificial intelligence system is allowed to act, not just suggest, the consequences become operational. A reasoning error can then trigger an event in the real world. A mistaken conclusion can become an unauthorized refund, an email sent, a database update that should not happen, a workflow escalation, or an infrastructure change. That is why the action domain matters. The action control domain governs what actions an artificial intelligence system can perform, what tools it can access, what application programming interface it can call, and what decisions it can execute autonomously. This is the domain where a model stops being only a reasoning engine and starts behaving like an operator inside the enterprise. The core risk here is the autonomous privilege amplification. The model may not have been designed to be privileged in a human sense, but once it is connected to tools, to workflows, and to service identities, it inherits the operational reach of those systems. If it can trigger a refund workflow, it inherits the blast radius of that workflow. If it can send messages to customers, it inherits the blast radius of customer communications. If it can initiate infrastructure changes, it inherits the blast radius of production operations. See, now you can start to see the problem and the risk, and that is the actual shift. In the cognitive domain, the question is what the model is allowed to think and generate. In the knowledge domain, the question then becomes what the model is allowed to know and surface. In the action domain, the question becomes much more direct. It is about what is this system allowed to do? And even more importantly, what irreversible actions can it perform without human oversight? That is the architectural question. A great deal of artificial intelligence conversation still centers on model quality, prompt quality, or response quality. Those conversations so matter, but action changes the equation. Once a system can execute, the security problem is no longer only about correctness, it is about authority. And authority is where blast radius accelerates. Let us look at the failure patterns that make this domain dangerous. The first pattern is unrestricted tool access. Many agent systems are built by connecting a model to a growing set of tools. The system can query a customer database, call an internal application programming interface, search documentation, run an automation script, update a ticket, send an email, and sometimes trigger a downstream workflow. Each additional tool makes the system more useful. It also makes the system more dangerous if boundaries are weak. The problem is not simply that tools exist. The problem is that they are often exposed too broadly. The model is given access to multiple capabilities without careful separation of risk. A tool that should only read data may also be able to modify it. A support agent that should only recommend a refund may be able to issue one. A workflow connector that should only open a ticket may also be able to close it, escalate it, or trigger compensation actions. At that point, the model is no longer only a conversational interface. It has become a privileged operator. And this is where the blast radius expands quickly and accordingly. Let's move to the second pattern. The second pattern is about over-permissioned service accounts. Normally, in enterprise systems, agents rarely act as themselves. They act through the service identities. Those credentials often sit behind the scenes and connect the agent to various parts. For example, they connect the agent to billing systems, to customer records, to automation platforms, to internal tools, and to administrative functions. In many cases, those identities were not really designed specifically for artificial intelligence agents. They were created for convenience, for integration speed, or because a broad service account already existed. Now you start to see that this is where the actual danger begins. If the agent inherits a service account with broad permissions, guess what? The blast radius of the model becomes the blast radius of that account. Easy concept, right? See, the reasoning engine at this point may appear narrow, the operational identity behind it may be broad, and because the system feels conversational, teams often underestimate the significance of that inherited authority. They think they are deploying a helpful assistant, but in reality, they may be deploying an execution layer with administrative reach. Now let's look at the third pattern, the irreversible automation. We all love automation. Automation is attractive because it removes friction and reduces human-prone errors. That is usually the point. So a support agent that can only suggest actions may save some time, but a support agent that can execute them may save much more time. As usual, the business case becomes stronger as autonomy increases. But the moment the system can execute actions automatically, reasoning errors stop being informational and start becoming operational incidents. A mistaken interpretation can issue an unauthorized refund. A misunderstood policy can send an incorrect customer communication. A malformed instruction can update a record, cancel a service, trigger a workflow, or apply a configuration change. Once the action is taken, it might be too late. The organization needs to deal with consequence, not suggestion. This is especially important because the failure may not look like an intrusion at all. There may be no classic compromise indicators, no attacker foothold, no malware, no suspicious login. The system simply executed the wrong action using legitimate pathways. That makes these failures harder for organizations to classify. Traditional security teams are trained to look for unauthorized access. Unfortunately, action domain failures often involve authorized access used incorrectly by an artificial intelligence system that was granted too much operational freedom. The last and fourth pattern is agent escalation chains. Modern systems increasingly do not stop at one tool call, they chain actions together. An agent queries a system, then calls an application programming interface, which triggers a workflow, which invokes another service, which may in turn notify another agent or update another system. Each step feels modular, each step feels reasonable. But together they create a network of autonomous decisions. This is where local errors become systemic effects. A single faulty judgment at the beginning of the chain may propagate across multiple systems. A refund triggers a customer email. The email triggers account tagging. The account tag triggers retention workflow changes. A prioritization agent receives the update and escalates the case. Now, multiple systems have been affected by one initial error. Do you start to see the chain effect? At this point, the architecture may look composable, and the blast radius becomes compositional. And unless boundaries are explicit, the organization may not even know where execution authority truly begins and ends. That is why action control requires more than general caution. It requires proper architecture design. And with that, let's shift from failure patterns to the actual design stage. If the action domain is where blast radius accelerates, then the design goal is to constrain that acceleration deliberately, not by hoping the model behaves well, but by limiting what execution paths are possible, under what conditions, with what credentials, and with what safeguards. The first control is action tiering. Not every action should be treated the same. Read access, suggestion capability, and execution authority are fundamentally different categories. An agent should usually be able to read information more freely than it can execute the transactions. It may be acceptable for the model to recommend an action, summarize a case, or propose a response. However, that does not mean it should be allowed to perform the action itself. This separation matters because it creates distance between reasoning and consequence. A useful pattern is to treat execution as a privileged state, not a default extension of reasoning. The model may retrieve information, it may analyze it, it may suggest an outcome, but the transition from suggestion to execution should not be automatic simply because the model sounds confident. That is where many systems fail. They collapse these states into one continuous flow. Think, decide, and execute. From an efficiency perspective, that is attractive. From a blast radius perspective, unfortunately, it is dangerous. The second control is scope credentials. Every tool connected to an artificial intelligence system should operate with minimal privileges. This sounds obvious. In practice, it is often violated. Agents are frequently wired into broad internal services because narrow scopes require more effort. Fine-grained permissions take time. Dedicated execution roles require design work, and broad service accounts make prototypes move faster. But broad credentials make blast radius larger. A support agent that only needs to issue low-value refunds should not inherit a billing role capable of a broad account actions. An infrastructure assistant that only needs to inspect the deployment status should not have production modification rights by default. A communication agent that drafts messages should not automatically send them to customers without scoped approval. The rule here is simple. Never give an agent the maximum authority of the system it touches. Give it the minimum authority required for its specific operational purpose. That is how you keep utility without silently converting convenience into privilege amplification. The third control is just-in-time authorization. High-risk actions should not be permanently available simply because a tool exists. Authorization should be evaluated at the moment of execution. This matters because context changes, user intent changes, and business risk changes. A refund may be acceptable at one amount and unacceptable at another. A communication may be harmless in one context and legally significant in another. A system change may be safe in a testing environment and catastrophic in production. Just-in-time authorization creates a checkpoint between intent and action. It forces the system to reevaluate whether execution is still appropriate under current conditions. In some cases, that may mean human approval. In other cases, it may mean policy evaluation, identity verification, risk scoring, or threshold enforcement. What matters is not that every action requires a human. What matters is that high consequence actions do not execute by default simply because the model requested them. The fourth control is transaction thresholds. Large or unusual actions should trigger safeguards automatically. This is a classic control principle that becomes even more important in artificial intelligence systems. Thresholds reduce operational blast radius by limiting scale and speed. A support agent may be allowed to issue a small refund under controlled conditions. That does not mean it should process 10 refunds in rapid succession without intervention. A workflow system may allow a limited update. That does not mean it should permit bulk modifications. An infrastructure assistant may be able to restart a single low-risk service. That does not mean it should roll changes across environments. Thresholds exist because many incidents are not caused by one catastrophic decision. They are caused by many small actions repeated quickly. Artificial intelligence increases that repetition speed. That is why transaction thresholds are not only financial controls, they are blast radius controls. The fifth control is execution sandboxes. High-risk operations should run in isolated environments whenever possible. If an agent needs to execute scripts, interact with automation tools, transform data, or test changes, the default environment should not be production. Sandboxing creates separation between decision and consequence. It gives organizations room to observe behavior, validate outputs, and limit propagation. This is particularly important for agentic systems because a tool use can create side effects that are difficult to anticipate in advance. A model may follow a valid local instruction, but still create a harmful system outcome when that instruction interacts with production state. Sandboxing reduces the chance that early errors become enterprise incidents. The deeper principle across all of these controls is the same. The model should not directly own irreversible authority. It may initiate a proposal. It may request execution. It may assemble context for action. But the architecture must decide when and how action is actually permitted. That is the difference between automation and uncontrolled autonomy. Now let's map this to our maturity level. At the ad hoc stage, agents execute actions freely with broad privileges. Teams are often focused on capability, not control. The system works, it looks impressive, but execution authority is poorly bounded. Tool access is broad. Service identities are over-permissioned. There is little separation between reasoning and action. At the reactive stage, controls appear only after incidents or close calls. A refund incident triggers a rule. A mistaken email leads to a new review step. A workflow error results in a hard-coded exception. Security improves, but only in response to failure. The organization is learning from consequences rather than preventing them by design. At the structured stage, the architecture begins to mature. Action tiering is explicit. Scoped credentials are enforced. The organization knows which agents can read, which can suggest, and which can execute. Execution paths are designed intentionally. High-risk tools are no longer exposed casually. Boundaries exist and can be explained. At the integrated stage, safeguards are embedded into workflows. Approval mechanisms, threshold controls, logging, and execution constraints are part of the operational design, rather than added later. Security review includes agent-enabled automation. Execution is treated as a control plane, not merely a feature. At the architecturally constrained stage, blast radius is evaluated during system design before the agent is deployed. Autonomous operations are deliberately bounded. Irreversible actions are gated. Privilege scopes are narrow by default. Escalation paths are understood. The organization can explain not just what the agent does, but what it cannot do and why. That is maturity in this domain. Not how sophisticated the model appears, not how many tools it can call, but how deliberately its action authority has been constrained. So what should different audiences do next? If you are an engineer, start by auditing tool permissions. Do not assume the connected tools are appropriately scoped simply because they are internal. Map what the agent can read, what it can propose, and what it can execute. Test edge cases in automation flows. Ask where suggestion becomes action and whether that transition is actually governed. If you are a security leader, review artificial intelligence-enabled workflows the same way you would review privileged automation. Focus on execution boundaries, service identities, and approval mechanisms. Ask whether the organization has accidentally created autonomous operators with business-critical authority. Require explicit design review for high-consequence actions. If you are an executive, ask one question. What real-world actions can this artificial intelligence system execute without human review? That question cuts through a great deal of surface-level optimism. If the answer is unclear, then the blast radius is not contained. And if the answer is broader than expected, then the risk is architectural, not merely procedural. Knowledge exposure is serious. But once artificial intelligence systems are allowed to act, reasoning errors become operational events. That is why the action control domain matters so much. It is where blast radius accelerates. T is where a mistaken conclusion stops being a bad answer and becomes a real refund, a real message, a real system change, or a real business consequence. Controlling that acceleration is now one of the central architectural responsibilities in enterprise artificial intelligence systems. In the next episode, we will move outward again. We will examine the system control domain where blast radius expands through infrastructure access, identities, and platform reach. If you are building or governing artificial intelligence systems in enterprise environments, consider subscribing. And until next time, stay secure and always design deliberately.